Thank you all for joining us today. We're going to go ahead and get started. So this is the Medical Center Libraries Research Workshop Series. My name is Stephanie Henderson, and I'm a medical librarian for the College of Nursing. And today we have with us our research data librarian, Isaac Wink. Isaac is going to be presenting 5 tips for managing your research data. This presentation is being recorded. And there's some other people joining right now. So let me just get them in. Great. So Isaac, go ahead and get started.
Great. Thank you very much, Stephanie. As Stephanie noted, I'm Isaac Wink. I'm the research data librarian here at UK Libraries, and I'm very excited to talk to you all today about some tips for managing your research data. Before we get started, there are a number of materials that I'm going to be referencing and resources to help you with your data management today. All of those are available in an online OSF project space, which you can access using the link below. Hannah is also going to be sharing links to these resources in the chat as well, so you can find them there. But also on this project space, you can find a handout which will include links to all of the substantive resources that I have for helping you with your data management. I also wanted to take a moment to talk some about the research data services that we offer here at UK Libraries. So if you need any assistance with creating and implementing a data management plan, either as a personal plan or for a grant, that's something I can help you with, as well as getting started with data management platforms if you want to look to make any changes to your workflow there or are looking for tools. I can also help with depositing and getting credit for your data in a variety of repositories, including those that align with the needs for federal funders like the NIH set forth in its new data sharing policies. And then I can also help with finding data sets for reuse. So if you think that there might already be data out there for whatever your need is, that's something that I can help you with. So I wanted to get started by thinking a little bit about how best to define research data management. And there are a couple of definitions that I wanted to share with you. One of my favorite comes from Kristen Briney, and it reads that data management is the compilation of many small practices that make your data easier to find, easier to understand, less likely to be lost, and more likely to be usable during a project or 10 years later. And what I like about this definition is it really highlights the way in which research data management is not one thing. It really is a set of practices that put together make your data well managed. Another definition that I wanted to point to is the UK data retention and ownership policy, just because it's one that governs all research that's conducted here at UK. And so it's one important for researchers to be aware of. And it lays out a number of different data management responsibilities that principal investigators or other research leads have. And these aren't all of those policies or all of those responsibilities, but a number of key ones are ensuring access to data, disaster preparedness, documentation, organization, and adequate preservation of data. I've also included a link there to the full data retention and ownership policy as well. And so now that we've talked a little bit about what data management is, why is it something that you should care about? The first reason are the various mandates that exist. One of those is the UK's own data retention and ownership policy, but also a number of federal funders like the NIH and NSF require active and robust data management practices that are carried out throughout the research data lifecycle. It's also important to keep in mind that it's possible for your data to be audited if there are questions about findings or analysis that you publish. And so having well-managed research data can make that process a lot easier and a lot less stressful. But there are a number of reasons that data management is also good for you as a researcher. One of those is that it can increase the impact of your research because data sets that are accessible and understandable are more likely to be reused and cited. If you share it in a data repository and include a citation for that, then it makes it, and if that data is well documented, then it makes it a lot easier for other people to reuse that data. You get a citation out of that, you can find potential new collaborators, and your work has a higher research impact. And then finally, it's important to keep in mind data management is good for research efficiency. I know that some of the things that we'll talk about today aren't necessarily the most exciting parts of the research process or the reason that you all became researchers, but what I'm trying to give you are tools to help with data management practices that you can implement to reduce friction in your research process and prevent problems that might occur down the line. That way you can spend a lot more time focusing on your own area of disciplinary study and the research that really matters to you. So today I'm going to go over 5 data management practices with an eye towards things that you can implement today or make part of your research habits or workflow without too much oversight or additional work being taken other than just that tactic itself. So as I go through these, my challenge for all of you today is to think about which of these practices is something that you could potentially introduce into your own research workflow or use to improve your own data management practices. The first one that I want to talk about is developing a file naming convention. And before we get into what that is, I want to talk a little bit about why it matters. And I think these 2 comics illustrate it very well. I'm sure we've all run into situations before, like the comic on the left, where either on our own computer or someone else's, we have just a very large number of files, but none of the names of them are descriptive. We have no idea of knowing what's what. And then similarly, in the situation on the right, I'm sure we've all run into a situation where we think that we're finally done with our analysis, our publication, our other research output, and then we need to handle additional edits, or we're constantly tweaking that process, that publication right up to the deadline. And then it can become confusing to know which version is actually the one that we're working on. And so these issues can be addressed if you have clear and consistent file names. In a best case scenario, without clear and consistent file naming, you might be a little bit annoyed at your own research processes. You might need to open a lot of files to make sure that you're finding the right one. But in more extreme situations, you may actually lose data entirely if you aren't able to locate it on your computer if you don't know its name, or if you're working with files with a lot of different versions to them, you might accidentally be editing an older version of a file, particularly if you're working with collaborators, and then your analysis might actually be spread across multiple different files. So a file naming convention is essentially just a set of rules for consistently titling your files. The goal behind a good file naming convention is to have something that you can easily apply to a project to make all of its various components unambiguous. And they look different depending on your own research needs or your own project, but there are a couple of best practices that apply across all different good naming conventions. The first of those is to make your names descriptive. File names are a chance for you to let yourself and other users know the contents of the file by including contextually important information. And what that information looks like is going to vary a lot depending on your research project. So for example, if your data files are interviews with participants, maybe you want to include a participant ID number in each file name so that you can easily distinguish between those. But that might look different depending on other data that you're working with. It's also important to have file names that you're keeping brief. As a general rule, it's good to keep them under 32 characters long and to use abbreviations. The reason behind this is if you try to fit a lot of different pieces of information into a file name and those file names get very long, then they'll get cut off in your file explorer on your computer. You won't actually be able to read them, and then you really aren't doing much good for yourself in making those file names descriptive if you're including too much detail there. So consider using abbreviations. For example, if you're collecting data from a metropolitan water district, you could abbreviate that as MWD. But it's very important to make sure you're also documenting any choices that you're making with those abbreviations. And we'll get into that a little bit later. And then finally, when you're naming files, it's important to make sure you're avoiding special characters like question marks, pound signs, @ signs, slashes, and spaces. Because all of these characters have special meanings in computer operating systems. And so sometimes they'll cause errors for a computer that tries parsing your file. In a lot of cases, your computer will give you a warning before you assign one of these to a file title, but not always. As a general rule, I like to keep to just letters, numbers, and underscores when designing my file names. So in the example I show down there, I connect different pieces of information using underscores. So putting this all together, let's look at what we could use as a file naming convention for a study that's measuring air pollutants in different US cities. So using those tactics that I talked about on the previous slide, what we have here are 3 different pieces of information that would be important to our study. The first one there is the date of data collection, and you'll notice that it's written out in the format year, month, day. And the idea behind this is that that's a much less ambiguous way of writing the date than writing it as day, month, year, or month, day, year, since depending on where researchers are coming from, they may interpret those dates differently, whereas year, month, day is a more consistently applied, or is a less ambiguous way of writing the date. And as we'll see later on, it can also help with sorting your data. And so in this study, we might also decide, since we're looking at different cities, to actually put the city information in the name of each of our data files. So in this case, we have Lexington, but if we had a city like St. Louis, for example, we would want to make sure we strip out any periods or other special characters in a name like that. And then finally, we have the pollutant being measured, in this case, lead, abbreviated with its atomic symbol, PB. So we have 3 pieces of information here that can really help us to preview the contents of this file well, and they're connected using underscores so that it's easy to distinguish those pieces of information from one another. So as I noted at the beginning, all of this is contextually dependent to what your own research needs are, and those can vary. When you're trying to decide how you want to order the pieces of information you put in a file name, one thing to think about is what's the most useful way for you to sort your data. In the screenshot on the left, where we lead with the date of data collection, you'll notice that this makes it a lot easier for us to sort all of our data by the date that it was collected. But we might decide instead that it actually makes sense for our workflow to group these by city of collection instead, as in the situation on the right. So there they still are ordered well, but instead of going by date first, it goes by city and then by date. And what works out best here really depends on your own research process. What really matters, though, is that you be consistent in the way that you apply these. So don't switch off between starting with date sometimes or starting with city sometimes. Then you're not going to be able to sort and organize these well. So I've included a link here, and this is included on the worksheet and in the project space, or on the handout and in the project space as well, including some guidelines on developing your own file naming convention. So that worksheet includes different questions that you can ask yourself about your own data and what needs you want to highlight in the names of the files. So some of the questions included there are what group of files do you want this convention to cover? Is this just for a subset of files? Is it for an entire project? Do you want to adopt a standard for your lab or research group? And then what information or metadata makes each of those files distinct? That is generally the information that you want to highlight in the file name so that you can tell them apart. Think about whether or not any information should be abbreviated to keep your file names brief and under that suggested 32 character limit. Think, as we discussed in the previous example, about what order you want the different metadata elements you include to appear in. And then make sure you're consistent with what characters separate each piece of information. Will that be an underscore? Will you use camel case or capitalization to separate them? Again, the importance there is consistency. And then finally, ask yourself if you need to track different versions of each file. If so, it's useful to include a version indicator in each of the files as well. That's a less ambiguous way of indicating where you are in the process than titling something final. And it also makes it easier for you to sort different versions so that if you need to go back to a previous checkpoint, you can easily. Regardless of what process you go with, though, you really want to make your file naming convention something for you that's very easy for you to implement consistently. One way to do that is to post a guide at your workstation or circulate it among your other researchers to make sure that all of the decisions you make there are documented, so it's easy to title these files the same way in every time. So that gets us to our next category, which is different means of documenting your data. So to think about why this is important, let's consider a fairly simple tabular data set here. Um, at first, these variable names look like something we can understand, but then some questions might start to appear about this data. So for example, in this time column, what units are we using to measure? Seconds, minutes, hours? There's really no indication just by looking at this table by itself. Same thing with age. It looks like these could potentially be days, but maybe we're actually looking at minutes here or some other measure of age. And then lastly, we have this 0 indicator under the heart rate variable, and it's not necessarily clear what that means. Does it mean that a measurement was taken and it really did read as 0? Did it mean that one was just missed? And these are things that we can't necessarily tell just by looking at a data set on its own. And that's why it's important to include data documentation in a variety of ways. So I'm going to go over 3 different methods of data documentation. These aren't exhaustive, but they're a good place to start. One of the first and most common of those is to develop a README file for a project. And the point of a README is to provide a description of files in your project to let users, including yourself in the future, know information that's important to the creation, organization, and use of those files, of the files that the README covers. So by convention, these are usually formatted as a plain text or TXT file. That way, you won't worry about any loss of information when files are converted to different types, since TXT is an open and very plain file format. You might encounter or create for your own project a project that has just a top level README that gives an orientation to the project as a whole, or you might see individual READMEs for specific subsets of files, blocks of analysis, that kind of thing. I've included a link at the bottom here to a guide from Cornell Data Services on developing README style metadata, and they include a template TXT file that you can use for filling in a README for your own project. But just to go over some of the information that's good to include there, it's good to include info about the project title and author contact information. That way, if people have questions about your data set, they know how to use it. Same with sharing and access information. It's good to be very unambiguous about under what circumstances people can reuse this data and if there are any limitations on it. And then it's also good to include a description of the folders and files and let people know what they can expect to find in there. And then finally, any methodological information about how the data was collected. So this is a sample README that I put together. This isn't all the information there, but as you can see, it includes the title of the data set that I made it for, information about me as the author, and then also information about the folders and files that people can expect to find inside. And what I want to emphasize about this is that some of the information you put in a README might be more useful for data sharing in terms of, you as the principal investigator probably won't need your own contact information. But it is good to include at the start and just to sort of be systematic about the way that you design them. But other information that you put in a README will be useful to you as a researcher and to the rest of your research team, such as descriptions of the folder list. That way, if you're creating a new file or you forget exactly how you wanted to structure things, then you have clear guidelines that you set for yourself that you can reference every time to make sure that you're sorting everything properly and keeping your data where it belongs and your project well organized. So another type of data documentation I wanted to talk about are data dictionaries. And a data dictionary is the best way of clearing up the ambiguity that we saw in this data set from the beginning. It provides human readable information about the variables that you collect to make sure that other users have important context for it, and people who are entering data or adding to that data set know how to format things. And I want to emphasize human readable here. Sometimes there are very good reasons for keeping data sets themselves very simple, but it's important to include supporting documentation that is easily navigable for a human reader. So this is what a simple data dictionary could look like for this data set. It would include the name of the variable, a definition of how each variable is used there, information about the units that the variable is formatted in, and then a description of how missing values should be entered. And you'll notice that this data dictionary could help us clear up some of those questions we had at the beginning. We know now how both time and age are formatted and what units they're calculated in. And we know that under heart rate, 0 indicates that a value is missing rather than it was collected and was actually 0. So that's a simple data dictionary. OSF provides guidelines on making a more robust one, and you can see in the screenshot here some of the other categories that they include. So in addition to the variable name as it appears in the data set, you can also include a human readable longer form variable name, information about how that variable is measured, any restrictions on its values, a definition, and the link there provides more information on how you can set up a data dictionary for yourself. Then the last documentation practice I wanted to touch on just briefly is code commenting. And this will look very different depending on what language you're using for writing scripts or other forms of data analysis. But it is important to keep in mind that it's a good practice regardless of what you're using, because it allows other people, and again, yourself in the future, to quickly understand what it is that different blocks of your code do. And you may think that these are things that you'll remember, or your script isn't all that complex, and so it's easy enough to do. But projects really do become a lot more complex as they go, and things that seem very rational or self-explanatory when you're in the thick of writing your code won't necessarily be when you come back to that a week later. So I've included guides to commenting syntax in both Python and R if you're new to those. But those practices can look different depending on what language you're using or what software you're using for coding as well. In addition, though, to the actual syntax of coding itself, another challenge here is it can just be difficult to set aside time for actually commenting things into your code. So what I like to do is try to make a habitual practice of setting aside 5 to 10 minutes at the end of any time that I've spent coding, where I review any blocks of code that I've either added or edited, and I'll write new comments for those or edit them if I've edited the code. That makes it a bit easier to make it a consistent practice. So the next thing I want to talk about is backing up your data, and equally importantly, testing those backups. Before I dive into that, though, I wanted to take a quick minute to talk about the difference between data preservation and data backups, because we sometimes see people using those terms interchangeably. The way that I think about the difference between them is that data preservation is a set of practices that are important for making sure that data remains accessible going into the future, both the short term and the long term. And preservation includes a lot of different things: bit level preservation, migration to new new storage media, conversion to new file formats, and also creating backups. And backups, is just the process of making copies of your files that can be used to restore your data if it gets lost or corrupted. And creating backups certainly is very important, and that's what we're going to focus on today. And it's an especially important element of preservation while the research process is ongoing, but it doesn't represent the totality of data preservation. So if you are thinking about how you're preserving your data, make sure that you are thinking beyond just there's a backup of it somewhere. So why does backing up your data matter? I think that a lot of us in our lives, we put a lot of trust in various cloud storage, whether that's Apple, Google, Microsoft, and it can be easy sometimes to just sort of assume that they have their own backup practices in place and are going to make sure that our data stays available. But that's not always a safe assumption. And a lot of researchers learned this in 2014 when the cloud service Deduce, which a lot of academics used for storing their research data, suffered a pretty catastrophic crash. And as the snippets of the article show here, not only was there a corruption to their primary data storage, but it happened at the same time that there was an outage with their backup system. So it was kind of a perfect storm. I'm not trying to single out any service provider here, but the point that I do want to make is that your research data matters. It's important to the work that you do. And it's so important that you want to make sure that you aren't just offloading all of the work to thinking about backups or of that data to a third party whose practices you might not fully understand. And so that's why it's good to make sure that you have your own backup practices in place. So the golden rule for backing up data is known as the 3-2-1 rule. And that means making sure that you have 3 copies of your data on 2 different types of storage media with at least one copy stored offsite. So one example of how this might look in your research process is that you primarily work with your data on networked storage as part of your department or IT systems here at UK, but you also, on a daily or weekly basis, upload your data to an external hard drive. So that makes sure that you have two different storage media that you're using. And then if you really want to be extra secure, then you could even keep a second external hard drive at an offsite location and swap out those two hard drives on a regular basis so that both of them are being updated on the data that they have. That way, if there is some really catastrophic physical disaster like a fire, then you would still have an offsite storage copy that you could restore your data from. So there are a number of different media options for you to consider when you're putting together your own backup policy. Some of the most reliable ones include personal computers, by which I mean, a laptop or another university-issued device, not necessarily a personal one that you personally own. External hard drives are a very good option as well. And then you can also look into local servers, either available through your college or through university IT. Or if you have a really large amount of data and you want to be very secure with it, there are access to offsite storage of magnetic tape drives. This remains a rather consistent form of data storage. The downsides of it is that those backups are harder to restore. It just takes more time since they're offsite and a lot of people don't have tape readers. But if either that or utilizing local servers, especially if you have a very large amount of data, are of interest to you, then UK Center for Computational Sciences are a good place to start at looking at those solutions. You want to avoid backing up your data on USB flash drives because flash storage degrades and corrupts a lot more quickly than other forms of storage like an external hard drive. So a flash drive might be appropriate if you just need to transfer files from one computer to another, but you shouldn't rely on it as something that you can put your files on a flash drive, put that in a drawer somewhere and forget about it, because chances are that if you come back to it and try restoring your data from there, the files might be corrupted. Also make sure that you avoid backing up your data on obsolete media. So it used to be somewhat common to checkpoint your data on CDs on a regular basis, but you may have noticed not a lot of people have CD drives anymore. And so while that may technically be a form of a backup, if it's not something that people can easily access in any way, then it's probably not a good choice. So I also wanted to address commercial cloud storage. We're a OneDrive campus here at UK, and you may also, either in your own work or in collaboration, use services like Google Drive or Box. And all of these can be really convenient options, especially when they can sync to your local device. They can make it easier to access your data or your research files from other devices. But there are some important things to keep in mind about them. One is that you should make sure you have an awareness of the terms of service that the service provider uses to make sure that it meets any privacy needs that you have for your data, especially if you're working with sensitive data of any nature. Also, be aware that sometimes the pricing models will change and can dramatically increase the cost of the storage that you're using. This happened with Google Drive a few years ago. They allowed unlimited storage for academic institutions, and then they revoked that policy and started limiting it unless people paid more money. And there was a long period of time in which people could get their data to other media, but a lot of people had really relied on that service and then were left scrambling when it came time to figure out another way of storing things. And then lastly, just keep in mind that if you use a synced folder, like if you have a local OneDrive storage on your computer, just keep in mind that deleting a file in one location will delete it in both. So it's not really a true backup in the sense of something that could be restored. If your computer gets exposed to a virus that's deleting files, and those two folders are linked between the cloud and your local computer, deleting them in one place may delete it in others as well. So you can use commercial cloud storage as part of your backup solution, but just make sure that it's not the only point you're using. So when you're developing your own backup policy, a few things that are good to keep in mind. One is to make sure that you're actually testing out these backups and confirm that you can restore data in the way that you expect to be able to. It's great if you have an external hard drive that you're backing up your data to every week, but if you do actually lose access to your data and need to restore it from that hard drive, you don't want to end up in a situation where you actually weren't backing it up in the right way, or the data is protected in some way and you don't have access to it. So do a test run just to make sure that you can actually restore your data if you need to. Additionally, as much as possible, try to make data backups a habitual part of your workflow. If this is something that feels really burdensome or onerous, then it's something that you're likely to skip out on when you're pressed for time. And so if you're able to have an external hard drive, you keep plugged in and then use it that way, and then automatically back up your data, or just set aside time on a weekly basis for making those backups happen, then that will make it a lot easier to do this consistently. And then lastly, remember that any number of backups is better than no backups. If you don't feel that you can keep to the 3-2-1 rule, do still think about other options for having at least one backup copy of your data that you can restore from if you need to. So the fourth tip that I'm going to talk about is developing research group policies for data management. And so if you are someone who collaborates with others, either in a lab group setting or with people at other institutions, it's important to keep in mind that everybody on your team has data management responsibilities, even if those aren't necessarily explicitly assigned. Even someone who's just doing data entry is going to be faced with questions of how do you format missing values, or how do you what code systems are being used. And so when you don't have those data management conversations explicitly, then people are just going to assume that what they're doing works out for the best. And that can lead to situations where maybe you have an enterprising grad student as part of your research team who created all of the files for you in OneDrive or Google Drive and owns all of those at the administrative level. But then when they leave the project, the PI and everyone else on the team loses access to all of those. That's something that can be avoided with clear ownership guidelines. Same with that situation I mentioned earlier of making sure that people have access to all the documentation they need, because if they don't, then you may need to go back and manually clean your data sets because everyone was formatting things in a different manner. And then lastly, we just talked about backups, and maybe those aren't taking place if everyone assumes that assuring disaster preparedness and data backups is part of someone else's responsibility. So I've included a checklist that I adapted for use at UK, which is also available in the project space. But I'm going to go over some of the elements of it here. The basic idea is to have a checklist to make sure you're having some explicit conversations about the different research needs or research data management responsibilities of different members of your team. That checklist goes into more detail, and I really like it just as a thought provoker to think about things that you might not even really be considering yet, but maybe should. I'll go over 3 of those sections here, and one of those is to explicitly define different data management responsibilities on your team. So know, for example, who's going to be the system level owner for any shared files. That should preferably be the PI, the research lead, or a similarly permanent investigator. This is actually a fairly common problem that I hear about people running into, of they just aren't thinking about who's owning files that are shared, and then they lose access to them when team members shift around. Other important responsibilities to explicitly outline are creating and updating documentation. So any README files, data dictionaries, code commenting that you're doing as part of a project, it's important to know who's responsible for that. Same with conducting data assurance and quality checks to flag anything that might be an issue before it becomes larger, as well as performing and testing backups to make sure that they work. So all of these responsibilities don't necessarily need to be part of a single individual's portfolio. They can be spread across multiple, but they're a good place to start in terms of thinking about how everyone on your team is playing a role in data management. Oops. Another thing that's good to consider is having onboarding and offboarding checklists for any new members from your team. So whenever a new person joins your team, it's good to make sure that they have all relevant data documentation guidelines. So for example, if you have a file naming convention, then make sure that any new team members have access to that, as well as the README, for example, or just have the opportunity to get oriented to the project. If you're assigning them any new data management responsibilities, make sure that those are explicitly outlined, that they understand what those responsibilities are, and that they have an opportunity to ask questions about it. And then finally, make sure that they have access to all the files that they'll need to complete their work, preferably at the start of the process. Sometimes this ends up being more of a piecemeal thing where people get access to files or they're shared with them on an as-needed basis, which can work sometimes, but in order to give a new researcher sort of a holistic picture of their role on a team and make sure they have all the relevant information, you can save yourself some headaches if you share all that info up front. And then similarly, make sure you're doing an offboarding process for any data management responsibilities for your team members. So review any responsibilities that were assigned to a departing team member and make sure that those are reassigned if necessary. That way, if someone was responsible for working on documentation, make sure you know who will be replacing them in that role. Do a double check just to make sure that they aren't the owner of any relevant files. If this is something that you're explicitly looking out for, hopefully it won't happen, but it is just good to do a double check and make sure that they transfer ownership of those files before they leave the team. And then lastly, make sure that you're removing access for departing team members from any systems or data that they no longer need. This can be particularly important if you're working with sensitive or private information. You want to make sure that people don't have access to that if they're not actively a part of a team and don't have an active research need for accessing that sensitive data. And so the last tip is going to be a little bit different than the others, but it's to self-audit any previously collected data that you have. And so in all of these tips that I've talked about, they really can be relevant to any different discipline, research type, or even those of you who work in various research support positions as well. But there is going to be a lot of variance across disciplines. And so your data management needs are going to be different from researchers doing other types of studies. They may also differ just based on the culture of your department and any local IT resources that you use for things. And then finally, they may differ just based on your own personal practices. And so what all that means is that when you're thinking about when you're evaluating your own data management practices and figuring out what you personally can be doing better or do differently, one of the best ways to do that and to evaluate how well you manage your own data is to look at the actual data that you yourself have collected in the past. Choices that you made then or assumed were obvious or didn't need explanation might no longer be obvious in the same way. So try picking a past project that you have, and depending on your level, that can be a course project, that can be data related to your thesis or dissertation, or related to a publication or another research output. One that you preferably have a little bit of distance from now, and just take a look at the data and ask yourself some questions about how well you think you manage that data on your project. So some general questions that you can ask in this space are, can you easily tell what's what in your project? Does the organizational structure that you chose make sense in terms of divisions into different folders? Is all of the data needed for the project represented in a single coherent place? Can you reproduce the analysis that the data in the project or publication that the data supported? This will look very different, again, depending on what discipline you're in. But one way to think about it is, what number of steps would you need to retake in order to reproduce this analysis? So if you're diligent about using scripts for data analysis, and those are well commented, and it's very clear to see what the analysis is doing at each step, then it may be possible to just reproduce that analysis instantly. The number of steps that you need to take there will vary a lot from discipline to discipline, but ask yourself, was there anything you could have done differently in this process to make it easier for others to see how you got to the results from the data? Are there any risks to your data getting accidentally deleted or corrupted? Are you storing this just on a personal device? Do you have a backup of it anywhere? If your device gets lost or stolen, are you going to lose all access to this data and all support for that publication? Or have you taken steps to preserve it in a data repository or elsewhere? And then lastly, in general, consider if you're prepared to share this data with a mentor or colleague or even an external auditor. So in other words, are you prepared to stand by the data that you've collected? Sometimes our personal data habits can be messy and, we may even feel a little bit of shame about just not doing things perfectly. And that's okay, but it is important to make sure that you are looking at these things with an eye towards, is this something that I'm ready to show other people? Is it something that I'm ready to feel proud of? And in the case of an external auditor, is it something where I can stand by the results of my research? Those external audits can be very scary and nerve-wracking and high stakes. And so as much as possible, it's better to ask yourself these questions about your data before you're in the thick of those situations. And then some more specific questions that you can ask yourself when self-auditing your data. Do the folder and file names that you chose make sense? Do the names match their contents? I really recommend going through and actually opening all of the files. So checking that your naming convention makes sense, but also just making sure you can still open all the files. Make sure nothing is corrupted. Maybe there's been an update to a software that you used for your data. So check to make sure that you can still open those files with any updated programs, and check if any information has been lost or if anything has been reformatted in a way that doesn't allow you to access it anymore. Are variables that you've chosen interpretable? Are their meanings documented and do they make sense? So do you include a data dictionary, for example, so that there's no ambiguity about how variables are measured or how they should be used, as well as what their values mean? And then lastly, just an overview question. Is there anything that you assumed at the time wouldn't need clarification in your project or in your research process, but now really doesn't make sense to you? And if there is, then that's something to consider for the long term to change with your current project or your next project of how you can avoid that happening in the future. So the last thought that I want to leave you with before we turn to questions and any discussion is that data management is a journey and not a destination. So unfortunately, you aren't going to be able to say, well, I spent a lot of time at the start of my project thinking about data management, and so now my data is well managed and I don't need to worry about it anymore. This is always going to be an ongoing process. It's not going to be something that you just do once and then forget about. But the good news is that you can make these processes a lot easier for yourself if you make them habitual, if you make using a file naming convention habitual, if you have templates ready to go for creating data dictionaries or README files or commenting on your code, if you institute a cultural practice in your research setting to work with to have conversations about data management as a research team. And all these things, all of these habits will hopefully make your research process a lot easier on yourself. It will avoid really catastrophic failures, as well as just day-to-day friction that can be frustrating in the process and make your research easier. So that's all that I have for you today. Thank you very much for attending. Feel free to ask any questions in the chat, or if you want to have a little bit of accountability for yourself, feel free to share in the chat if any of these tips particularly resonated with you or something that you want to try implementing in your data work currently. And then I've also included my email address there so that you can get in contact with me if you have any questions about today's presentation or have any more specific data management questions for your own project. Feel free to send me an email or contact me through the Research Data Services at UK Guide, which was shared at the beginning here. So thank you all very much.
Thank you, Isaac. These were some great tips, and I know that I will be implementing some of these in the future soon, very soon. So if anyone has any questions for Isaac, feel free to put them in the chat, or you can raise your hand. There's some messages in the chat, Isaac, if you can see them.
Yeah, thank you, Cynthia. I'm very glad to hear that this was helpful. And Paul, yeah, definitely agree that offboarding is something that we often don't think about in the research process. And I truly just want to reiterate, one of the most common data problems that I hear about is people not realizing who was the institutional owner of a Google Drive folder or OneDrive folder or Lab Archive notebook. And then, a postdoc or a research assistant leaves a project and then people no longer have access to it. And really with all the elements of that checklist, what I think is really important is just to make explicit some of these roles that people on your team are already playing, just to make sure that there are no assumptions getting in the way of how you as a PI or just a member of a research team think things should be implemented.
And there's a question from Helen.
Yeah, and I'll agree with that. So can you talk about how you could teach students to use these tips in a class session that involves student research projects? That's a really good question because, I think it's something important to keep in mind for both undergrad and graduate education that those classes can be important places to make explicit some things that will be important when those students are serving on research teams. And in terms of projects for that, I've got a couple of different ideas. One of those is to actually make a deliverable in the class be, development of a README file for a project. That could be either at the start of the project as sort of part of the data management planning step, or it could be at the end. So, around the time of final presentations, maybe ask students to also provide an accompanying README or other form of documentation. Another thing that I think can be very useful to do is if you're in a discipline that practices data sharing, actually go through the process with your students of searching through some of those data repositories and looking for data that other people are sharing, and then ask questions as a class or have them ask questions individually about how they would grade the data management of the people who are sharing that data. What a lot of disciplines are getting better at data sharing as a principle, but if you do dig into some of the outputs that are being shared there, sometimes they're not the best formatted, or there's not good documentation, and those are real hindrances to actually reusing them. And that's something, or either of those assignment types are something that I would be happy to come in and do with classes, particularly when it comes to searching data repositories and thinking about some of the analysis and data wrangling work that needs to be done to get those into a usable format for data reuse.